Hello and welcome back. We're going to work in this video with more practice on how we deal with the change or the change in velocity in this case, or expressing vectors in two dimensions. So recall that in one dimension we could just use a plus and a minus to keep track of the direction part of the vector, but in two dimensions we need to employ a coordinate system, and this is what we want to get comfortable with practicing. Positive and negative is no longer sufficient because now we have lots of different directions we can go when we are allowed to move within a plane. So what I've done over here is define an initial velocity and a final velocity, and both of them are being defined in mad form. And I want to know what is the change in the velocity for this object. So this is the goal. And remember that the change in the velocity is the final velocity minus the initial velocity. So we're going to be dealing with vector addition and subtraction. And recall that I don't like to memorize how to do subtraction, that I can actually write this as v plus a minus v naught. Okay, those are of course exactly the same expressions written slightly differently. So these are both the mad forms, but we can only add and subtract in component form. So first of all, let's actually represent these vectors as they exist in a coordinate system, and then let's put those vectors in component form, and then we can actually perform the subtraction or addition, either way you'd like to look at it. Okay, so here is our coordinate system. And here is the y-axis and the x-axis. And our initial velocity is 10 meters per second at 98 degrees. So I start at 0 degrees and 98 degrees, go out 10. That is our vector v naught. This angle right here, 98 degrees. Our final velocity is 12 meters per second at 290 degrees. So here's 180, 270, 290. So our final velocity, a little bit longer in length because it's 12 as opposed to 10 meters per second. And so this is our final velocity v. And this angle here is our 290 degrees. All right, so there's the two vectors expressed in the coordinate system. Now I'm going to take each one of them separately because I need to figure out the component form of these vectors. And remember, I just used the trig functions and right triangles to do that. So first of all, let's take the initial velocity v naught, and that initial velocity v naught is like this. So there is v naught. And notice that v naught can also be expressed as how far to move along the negative axes and then how far to move up in y, or conversely, and you get exactly the same triangle either way, first of all going up y and then along negative x. So either one is fine. We will start off going along the x-axis, so I can re-express vector v naught as a vector that is pointing along the negative x direction added tip to tail to a vector that's pointing along the positive y direction. So this is going to be my initial x piece, and that's going to be my initial y piece. So I know how long the hypotenuse of this triangle is, and I also know this angle right here. This angle right here is going to correspond to this angle. This angle is 180 degrees minus the 98 degrees. So I know this angle. So let's take this little triangle and let's blow it up. Make it nice and big. Okay, and this side is 10 meters per second. And this angle right here is going to be 180 degrees minus 98, which is going to be 82 degrees. So this angle right here is 82 degrees. So notice that I can get v naught x and v naught y by using sine and cosine. So v naught x is going to be equal to v naught, which is 10 meters per second, times the cosine of 82 degrees. And V naught y is going to be equal to 10 meters per second, the hypotenuse, times the sine of 82 degrees. So using these two forms, I'm able to now get the MAD form of, or sorry, the component form of vector V naught by using, these are just some numbers, and I don't have my calculator, so I'm not going to work out exactly what number that is, but I can express vector V naught in component form as 10 meters per second cosine 82 degrees along the negative x direction, so remember that's minus x hat, and then plus 10 meters per second times the sine of 82 degrees. And now that's going to be along the positive y direction, so that's y hat. So now I have V naught in component form. Now I need to get vector V in component form as well. So let's take vector V and draw it in its own coordinate system as well. So here's vector V. Here's the y-axis and the x-axis. And I can give the information about vector V as how far we need to move along x, added tip to tail to how far to move along negative y. So this is vector V. We're going to call this the piece that is along the, the x-axis, Vx, and a piece that's along the negative y-axis, Vy. So I can take this triangle and blow it up down here, and I'm going to do that. So there's that triangle. And remember that this side is 12 meters per second. And I know this angle right here, right? I know this angle right here is going to be the 270 subtracted from 290. This angle right here is 20 degrees. So if this is 20, then that means this angle is 70. So this angle right here is 70 degrees. So here is my Vx and my Vy. I can find the component form of each Vx and Vy by using sine and cosine. So Vx is going to be the 12 meters per second times the cosine of 70 degrees. Vy is going to be the 12 meters per second times the sine of 70 degrees. Okay, so notice that those two added tip to tail gives you vector V. So the component form of vector V then is 12 meters per second times the cosine of 70 degrees. And that's going to be along the positive x direction. So that's x hat. And then added to the magnitude along y, that's 12 meters per second times the sine of 70 degrees. And that's along the negative y direction. So that's going to be minus y hat. All right, so again, these are just some numbers, right? We can plug them into the calculator and get the exact values. We're not really necessarily worried about that at this point. The method is incredibly important. We want to be focused on that. Okay, so the change in the velocity is equal to V minus V naught. We now have these vectors in the form that we can deal with addition and subtraction. The only way you can add and subtract is in component form, and we do have them in component form. So then we have vector V first, which is going to be our 12 meters per second cosine 70 degrees x hat plus 12 meters per second times the sine of 70 degrees minus y hat. And now subtracting V naught, so minus, and now I need to open up parentheses because I'm going to have to distribute that negative sign through the parentheses. So 10 meters per second cosine 82 degrees minus x hat plus 10 meters per second sine of 82 degrees y hat. end parentheses. All right, so there it is. Delta V then equals, and I'm going to combine the x's together. So what do we have that is being multiplied by x hat? Well, we have the 12 meters per second times the cosine of 70 degrees. And then this minus sign and this minus sign are going to give me a plus. So this is going to be plus 10 meters per second times the cosine of 82 degrees. So there's my x hat piece. And then we're going to have plus y hat. And what do we have for that? Well, first of all, we have a minus 12 meters per second times the sine of 70 degrees. And then minus a plus is going to give me another minus sign, minus 10 meters per second times the sine of 82 degrees. So there's the piece along x and the piece along y. You can see that delta V should have a positive x piece and a negative y piece by simply looking at the parentheses, what's in the parentheses here. And just graphically, if we were to find what V minus V naught is graphically, remember that I can represent delta V graphically as V plus a minus V naught. So if I represent that graphically, I take vector V and I draw vector V here. And then I take a minus V naught, so remember that I have to flip the arrow around and I can place them tail to tail, so minus V naught is going to be like this. Okay, so again, the arrow goes on the other side. And then completing the parallelogram, we're not going to catch that all the way, but you can see that that is going to be pointing in the fourth quadrant. The fourth quadrant, x is positive, y is negative. So this vector graphically can be seen as a vector that is in the fourth quadrant. All right, we'll see you next time.